Saxon Algebra 1, Lesson 70. Students, today we're going to talk about a type of mathematics that is not algebra, and it's not geometry. It's from the world of statistics. Statistics is the study of groups of numbers, and it's a discipline in which we organize the numbers and create new numbers in order to make sense of a big body of data to help interpret it. If you follow any kind of sport, you know a lot about statistics because every sport is dripping with runs batted in and assists and interceptions and all kinds of data that we manage about the teams we care about, and they're all different types of statistics. Probability is a type of statistic that you don't see a lot in sports as we practice them. It is sometimes referred to as game theory because probability is a tool we can use when there's an equal chance of something happening. Okay, so it involves things like rolling dice, flipping coins, spinning a spinner like, what's a game that has a spinner? The Game of Life, I think, has a spinner, doesn't it? Hi-Ho Cherry-O, I can guarantee you has a spinner. So that's what we're talking about. Usually when we're talking about probability, we're talking about games of chance. And I'm going to give you a formula, but it will make a lot of sense of it in a minute. The probability of something happening is created as a fraction by taking the number of desired outcomes. And I know these words don't make much sense. Wait till we get to a problem. You'll be like, oh, that's easy. Divided by the number of total outcomes possible. Like I said, that's word soup. Don't let it psych you out. It's really easy, and I'll explain in just a second. Okay, let's take the simple case of flipping a coin. And specifically, we're flipping a coin and we want to know the possibility of getting heads. Okay, this reminds me of at the beginning of football games, you know how they flip a coin to see who's going to kick and who's going to receive, and then it reverses for the second half? Well, there's two outcomes, right? Heads or tails. That's the only thing that can happen when you flip a coin. You're going to get heads or you're going to get tails. So there are two possible outcomes. As the team who gets to call the flip, what is it, the visiting team? I think that's what it is. They call what they want. They only get to choose one of them, right? So the probability of getting heads, if that's what you choose, is 1. You only have one desired outcome. It's got to be heads. And there's two possible outcomes. So you have a 1/2 probability of getting heads, or sometimes we say it as a 50-50 chance. We're not going to use this kind of language in math because we're studying it from a more mathematical point of view. But this is the way we talk about it, right? We say, oh, you have a 50-50 chance of throwing heads, right? Or of getting heads when you flip the coin. Yeah, because there's one outcome we want out of two possible. So that means it's half, and 50-50 is another way of saying saying half, right? Okay, let's take a look at a couple examples. And these, you guys, these are fun problems. They do not really get very hard. All right, let's see what 70.1 says. A fair coin. Okay, let me tell you what a fair coin is. A fair coin is a normal coin. Did you know that there are places in the world, don't ask me where, because I've never looked into it, but there are places in the world where you can buy an unfair coin. You can buy a token that looks like a penny, a nickel, a dime, a quarter, or whatever, except it's not an actual coin because it's weighted. It's weighted so that one face of the coin is heavier than the other. I assume you could buy them so that they're weighted so that you'll get heads more often, or they're weighted so you can get tails more often. But that is not a fair coin. That is a cheater's coin, my friends. And so what John is saying when he says a fair coin is he's saying there's no cheating going on here. This is perfectly on the up and up. A fair coin is tossed 3 times and it comes up heads every time. What is the probability that on the next toss it will come up heads? Okay, let me draw a picture of what we're talking about. We're tossing the coin once, twice, 3 times, 4 times. And what we're saying is that it comes up heads, heads, heads on the first 3 times. And we want to know what it's going to come up on the 4th time. Well, here's the thing about probability that takes a minute to sink in, but it's true. The kinds of games that we're talking about where there's an equal chance of something happening means that whatever's happened in the past does not matter. The fact that we've had 3 heads in a row does not tell us anything about the fact, about what we're going to get on this 4th toss. They are what's called independent events. I'm going to slide the book up so you can see it a little bit better. Tossing a coin is an independent event. So the 4th toss has the exact same probability of being heads that any time we pick up a coin and toss it. So it's 1 out of 2, which we just figured out here, but we can figure out again. Tossing heads is there's 1 outcome out of 2, heads or tails, right? So it doesn't matter what has happened in the past. All that matters is that we are independently tossing this coin, and the probability of getting heads is just the same as any other time. It is 1 out of 2. Now later we're going to address the question, what are the odds of flipping a coin and getting heads 4 times in a row? That's a different question, and we'll talk about that later. But right now we're saying you got heads, heads, heads. What are the odds you're going to get heads again? And some people would like to think, oh no, it's better than that because you've gotten heads so many times. Nope. Every single time we flip the coin, it's called an independent event. And what has happened in the past does not matter. Let's do another one. Example 70.2. 6 green marbles and 8 red marbles. Oh, look. 6 green marbles. I love doing this. And 8 red marbles are placed in an urn. You know what an urn is. It's like a big vase. 1 marble is drawn and then dropped back in the urn. Then a second marble is drawn and dropped back in the urn. Both marbles were red. If another marble is drawn, what is the probability that it will be red? Okay, like always, we want to draw a picture of what's happening. 3 times we're drawing from the urn. The first time, we got a red. It is not necessarily to write this in color. I'm just having fun. And so now we want to know what is the probability of drawing red here. Again, this result does not matter. We don't care. Drawing a marble out of an urn is an independent event. And every time you draw it, you have the exact same possibility. So the probability of getting red is 8 out of the total number of outcomes, 14. And we can reduce that because that's always fun. 4 out of 7. Okay? So the probability of drawing a red marble is 4 out of 7, no matter how many you drew in the past. Cool, right? Oh, I have to draw my annual picture of an urn. An urn usually is kind of fancy. It kind of goes, I always think of them as having like a bell shape and then a foot on the bottom. And they're fun to try to draw because they're hard to make symmetrical. They have a base like that, and then they have an opening up here. My marbles are down in here, and we can shade it a little bit to try and make it look kind of dimensional, right? It's dark on the inside. All right, that's an urn. And that's what our marbles are in. We haven't lost our marbles, they're in the urn. Okay, so now I've drawn my urn and I feel good. All right, example 70.3. A single die is rolled 3 times. Okay, let's just, it helps to draw pictures in these. I'm not just doing this to be crazy. It helps because it helps us imagine how we're drawing the outcomes. Oh, my die just went crooked. Okay, there's my die. Pretend it's perfect. I think this needs to be a little bit more like that. Okay, there it is. You know what a die looks like. 1, 2, 3, and then 4, 5, and 6, right? We don't have to draw all the sides. It's rolled 3 times. The results are, oh, and John drew cute little pictures, 1, 4, and 3 in that order. What is the probability that the next roll will produce a number greater than 2? So what's the probability of getting greater than 2? Okay, that's how I write the question. I write the big P for probability, and then I make some little shorthanded version of what the question is about. All right, this actually helps if instead of drawing a cute 3D version of a die, I draw a map of the 6 different faces of a die. We get to make the dots. That's the fun part, right? 1, 2, 3. I think I got the angles backwards. I think 2 goes this way and 3 goes that way, but it's okay. 5. Did you guys ever play that game Trouble? I'm pretty sure it still exists. We had it when we were kids. My brother got it. And it's got that little dome, and instead of having the die rolling around loose, you just push down on the little plastic dome and it pops the die so that they go. It was called the Pop-O-Matic Dome. It was always my favorite. I love a Pop-O-Matic Dome. Okay, so here are our 6 possible outcomes, right? Okay, and remember that the probability of anything is equal to the number of desired outcomes over the number of total outcomes possible. Now, this is my shorthand version. Okay, we are looking for the probability, I don't need an equal sign there, the probability of getting greater than 2 is, okay, how many scores will give us greater than 2? 3, 4, 5, and 6. That's 4 scores. 6 possible outcomes. But what about the fact that we've rolled a 1 and a 4 and a 3 in the past? Does not matter. Rolling a die is an independent event, so previous events do not affect the probability of the more recent, and then we can reduce this to 2 over 3. We always reduce when we can. Just like every other time in math life. Okay? Desired outcomes over total possible outcomes. All right, now we're gonna up it. Because, you know how I talked about Trouble, that Pop-O-Matic game? That didn't use 1 die, it actually used 2 dice. So let's consider a problem with 2 dice. And is this our last one? Oh no, we get to do the spinners. Okay, so this time in example 70.4, I hope you're having fun drawing these pictures. That's the best part of this lesson. 2 dice are rolled. What is the probability that the sum of numbers is A, what's the probability of 7, and B, what's the probability that the number will be greater than 8? okay? What's the probability of rolling a 7? What's the probability of getting greater than 8? Now, here's the thing about rolling 2 dice. There are a lot more answers than just this simple 1, 2, 3, 4, 5, 6 thing we drew back here. In order to understand what's happening when we have 2 dice, we have to draw a bigger chart. So draw with me. Once you know how to draw this, it's fairly easy to recreate, but you really can't do this in your head very well. So stick with me. Oh, I don't think I drew enough lines. 2, 3, 4, 5. Okay, we want to be able to skip the top row and write 1, 2, 3, 4, 5, 6. Okay, and then we're going to do the same thing up here. I'm going to divide this into 6 columns with wiggly lines, but that's okay. The math will work just fine. Whoa! And then we go 1, 2, 3, 4, 5, 6. Okay. Each one of these represents one of the 2 dice, right? So imagine that we're playing, let's play Monopoly this time. You roll 2 dice. If you get 2 ones, what is your move? How many spaces do you get to move? Well, you add them together, right? So that's 2. And what I'm gonna do, just so that it helps us, is I'm gonna do a double line here so that we won't get confused between the graph or the table and the results. Okay, if I roll a 1 and a 2, I get to move 3. A 1 and a 3, I get to move 4. You see what I'm doing. You're just adding together the numbers, right? If I roll a 2 and a 1, 3, and you can see that it's pretty easy to fill this table in. A lot of you, I bet, are thinking, this is dumb. I don't need to write all this out. But when you see how we're going to use it, you'll go, okay, so maybe, well, maybe you won't, but I'm telling you, you can't do this in your head. Trust me. 6, 7, 8, 9, 10, 11, and we see really nice little patterns coming. 7, 8, 9, 10, 11, and here it is, double boxcars, 12. Okay, now we have this table that shows us all of the possible outcomes from rolling 2 dice, right? We can get anywhere from 2 up to 12 depending on what number shows up on each of the dice. So what's the probability of getting a 7? Well, we just go through and look how many times did we get 7? 1, 2, 3, 4, 5, 6. The probability of rolling a 7 is 6 out of how many in all? 6 times 6, 36 odd, 36 possible outcomes. And so that's a 1 out of 6 chance of rolling a 7. That's correct. Now, what about the probability of rolling greater than 8? So that means a 9, a 10, or 11, or a 12. I'm going to use a different color just so you can tell one answer from the other. What did I say? Greater than 8. So it means 9s, 10s, 11s, and that 112. So how many scores did I circle? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of the 36 possible scores, totals, what did I say? 10. 10 out of 36. So the probability of rolling greater than 8 equals 5 out of 18. Right? 10 scores are possible, 36 are the, I'm sorry, 10 scores are desired, right? Because we want it to be greater than 8. 36 are possible. That's how I got this, and then I just reduced it here. These are both correct. All right? This little chart may seem like too much trouble, but once you write this chart down, finding the answers are really easy. And I can tell you, I had this problem on a test for a long time, and you'd be surprised how many people got it wrong because they didn't want to write the chart out. They tried to do it in their heads. Even having seen this problem like this and doing a few in the homework, they still thought they could get away with not doing it, not writing it down and just carrying it in their heads. And I'll tell you what, it's a great way to get a problem wrong. And many, many times it happened. Okay, so let's talk for a minute. I want a fresh page. Let's talk about what I mentioned before. Let's call it designated order. And that's when we want to find the probability of not just one thing happening, but a series of things happening. And I'll show you how it works. A fair coin is tossed 4 times. Okay, so here are our different events. 5 times the fair coin is tossed. No one's cheating. What is the probability that the first 2 times it comes up heads, and the last 2 times, oh, I made 5, that was unnecessary. The last 2 times it comes up tails. Don't need that, sorry. Okay, now, this is different than what we did before, because last time we said, this is what happened, what are the probability that it will be tails this time? Now we're asking a different question. We're saying, what are the odds that you'll get this whole pattern of events? And here's the way we calculate that. We find the probability of each individual event, and we know the probability of getting heads, well, that's 1 out of 2. Heads is 1 out of 2. Tails is also 1 out of 2, right? And to find the combined probability of getting all these things in a row, we multiply them. And so our final answer is 1 out of 16. And the way we can write this is to say the probability, I'll write it here, of heads, heads, tails, tails equals 1 out of 16. Right? We can just make up little codes of what we want to write there. Okay. Example 70.6 is a similar designated order problem. And this is our last problem. This one involves a spinner. Hi-ho Cheerio style, just like I'm telling you. Only this one has, I think that one has pictures, doesn't it? Pretend this is perfect. That's not perfect. This one has numbers in it. And it's got the little arrow thingy, you know, that you flick and you hurt your finger. Got the little plastic arrow thingy, and it goes around and it lands. It never really works all that well, but whatever. We're pretending that this is like a state-of-the-art spinner, and so it goes around seamlessly and it comes up beautifully. I'm suddenly thinking of Wheel of Fortune, that TV show, and you know how they spin that big wheel? It's supposed to be randomized, but I have heard people say that it's weighted and that somebody off camera can control where the wheel stops, which makes me very sad. But that would be, right? We can't apply game theory to a game unless it's completely fair. So I don't know if Wheel of Fortune would apply to this, but our spinner is completely fair, and when you spin it, it goes around perfectly and effortlessly, and it stops of its own volition, and no one's cheating. What is the probability that the spinner stops on 4 and then 3? Okay, well, we find the probability that it will stop on 4, and then we multiply that by the probability that it will stop on 3. So we have to find each of these probabilities. A probability is equal to the number of desired outcomes over the number of total outcomes. So if we're looking to get a 4, that's a 1 out of 4 chance, right? What about the probability of spinning a 3? Well, that's another 1 out of 4. So the probability of getting a 4 and then a 3, we multiply. 1 out of 16 equals the probability of a 4 and a 3. Yay, that's the right answer. Okay. Games of chance, fair games of chance, where no one's cheating or rigging the system, follow these very simple rules of probability. Remember that if you're looking at one event at a time, like we were here. If you're looking at just the probability of one event, then the other ones don't matter, right? The probability of flipping, what were we looking for? We were looking for heads, and we'd already thrown heads a bunch of times. It's okay, that doesn't matter. It's an independent event, so we don't have to pay any attention to that. That's different than what I'm talking about here, where we're looking at not just what's the odds of throwing tails once, but what's the odds of getting that pattern of heads and tails. And we found out that it's 1 out of 16 to get all 4 of those to fall that way. Okay, I hope you have fun with this lesson. Most students find it kind of a relaxing break from the trinomial square root business we've been up to our ears in otherwise. So enjoy these. I hope that when they come up in your homework, you go, oh, okay, good, a break from the crazy. All right, that's all. Thank you, goodbye.